Okay, we're going to start talking about parametric equations. It's a different way of graphing equations, essentially. So parametric equations are when you have an x equals and a y equals, and then both of them have a t value, which represents time, I guess, in theory. So the reason that we're going to learn about parametric equations is because sometimes rewriting a function as parametric equations is much easier, and working with that is much easier to do calculus such as derivatives or area or whatnot. So we learn parametric equations so that we can deal with it. For example, like a circle is much easier to work with in parametric equations than it is in Cartesian coordinates. Because you don't have to deal with square roots or anything like that. You're just dealing with trig stuff, which is, believe it or not, much easier to deal with square roots. So we're going to go ahead and go through it. All we're going to do is we're just going to make a little table of values, and we're just going to sketch this function. And then I'll go ahead and solve this into Cartesian coordinates so you can kind of see what the relationship is. So if I were to just make a little chart here, so if t equals this, well, what is x equal? What does y equal? We'll plot that point. So I usually start with 0. If there's no restrictions, then I usually just start with 0. Some problems, I'll show you here in a second, will tell you exactly what the time restrictions are. Like this one coming up will tell us, oh, we start negative. This one doesn't tell us, I just start with 0 and work my way from there. So I plug in a 0. Plug a 0 into x, I get roots -1. But you can't do that, so you can't plug in a t equals 0. T equals 1. Well, that will work because x will be 0 and then y will be 3. So I'll plot that real quick. So 0, 3. Plug in like a 2. Plug in a 2, x is 1, and then y is going to be 4. So here we go. Plug in a, well, I don't want to plug in a 3 because I don't know how to. I don't like sketching a root 2. So the next nice pretty number here to plug in, probably not 3, not 4, 5 would work. So 5 is a nice little number there. So plug in a 5. I'm going to get root 4, which is 2, and then I'm going to get 7. So 2, 7. So 1, 2, 3, 4, 5, 6, 7. You can kind of see the shape it's making right now. Okay, so this is definitely making a half a parabola, and it's going in this direction. So if you notice, I put an arrow at the end and in the middle, just meaning that, hey, this is our direction with time. Okay. So let's go ahead and solve for this so that we can figure out, oh, what exactly is going on with this graph? How can I make this into Cartesian so we can understand what the heck this actually means? So what we're going to do is solve for t and then substitute it out. So it doesn't matter which one you solve for. I'm going to solve for this t on the y side because to solve for this t, I'm going to have to square things and move things over. It's a mess. So it's easier just to solve for this t. So I'm going to just move that 2 over so that t equals y minus 2. Okay? And I'm going to go ahead and plug that into here. So now I have x equals root y minus 2, and then that minus 1 right there. So that's all I'm doing, just substituting in. Now it's in terms of x's and y's, and boom, we are officially Cartesian. But I'm sure you're looking at this and you really don't know exactly what's going on, so you probably want to solve for a y equals because you're just familiar with a y equals. Not so much of the x equals. So let's go ahead and move this on over. So, well, simplify this before I move anything over. Y minus 3. Also, I'm going to give you a little restriction here. X has to be bigger than or equal to 0. Since this is a square root, x can never be negative. Okay? So I'm going to add this little restriction right there, something that we're not really used to, but with parametrics, we're going to have to add some restrictions. Okay, even in my table right here. You saw that in my table, 0 ain't going to work. All right, when I plugged in 1, that was my lowest x value. So from here, let's go ahead and square both sides. So I'm going to get x squared equals y minus 3. Again, that same restriction. X has to be non-negative. And then move that 3 over, and I'm going to get x squared plus 3 equals y, with this restriction of x has to be non-negative. And this is actually, I'll rewrite this so it's y equals in front because that makes people happier. So there you go. All right. So pretty much, here's some little notes. If no restrictions, follow the curve to the ends of the graph. Layer on a restriction only if the new equation does not provide a restriction. So I had to layer this restriction because x can never be negative. So this is the parabola, half parabola, which you can kind of see right there from pink already. Okay, so this is like one example where like these parametric equations are not easier to work with, but I'm just trying to familiarize yourself with them for when we start to do the calculus. And then also parametric equations are so much easier to work with when we start talking about, again, velocity, position, stuff like that. So much easier. All right, let's go ahead and do two more. Really the same exact idea here. We're going to go ahead and sketch it using a table. This one's not so bad, but this one might blow your mind a little bit, so I look forward to that one. So quick table here. So t, x, y. So I'm going to go from -2. Am I going to really do all these numbers? I guess so. -2, -1, 0, 1, 2, 3. We can kind of figure out what the heck is going on here. Okay, so if I plug in a -2 into x, I'm going to get 1. Into y, I'm going to get -4. If I plug in a -1, I'm going to get -2. And then plug in a -1, I'm going to get a -2. So I forgot to sketch these along the way. So 1, -4, -2, -2. And then if I plug in a t equals 0, I'm going to get -3, 0. So -3, 0. Plug in a 1, I'm going to get -2, 2. So -2, 2. So as you can see, this is not a function, because we're going to have the same outputting here. So that's why parametric equations are a little bit easier to work with this one, because since this is not a function, it's hard to take the derivative of certain parts of it, whereas parametric equations, we can just take the derivative at certain times. It's not a big deal. Plug in a 2, looks like I'm going to get 1, which is also a value we already used in x equals value. 1, 4. And then plug in a 3, I'm going to get 6. 6, 6. 1, 2, 3, 4, 5, 6. Up here. There we go. So I start here. And then I actually have an ending point, so I'm not going to draw out the arrow at the very end. All right, so I'm done here because my time said you're done. It's over. But I'll put a couple arrows in here to let you know which way we're going. So we start there, we're going in that way. Okay. So what the heck does this look like as Cartesian? It is going to be kind of sort of weird. All right. So again, solve for t. That's what I would do. So let's solve for t. So in this case, t is going to equal y over 2, and then plug that into here. So x equals y over 2 all squared. And then, minus 3. So we're going to get x equals y squared over 4 minus 3. And that's it. That's really, you can't solve for y here because you give that squared. So this is really it. But there is a restriction. What's my restriction? So your restriction that we always do, by the way. So if you look at the previous example, since this was a y equals, I'm restricting x. This is an x equals, so I need to restrict y. So let's look at my chart right here. Here's my lowest y, there's my highest y. So I'm restricting y from -4 until 6. So there's my restriction there on y. This one's easier to do just by looking at this because we have a specific time restriction. Okay, so that's why I'm able to just go from here to there. So since this is giving you a restriction, I have to input this restriction as well. So next one. So now this is one that scares people because I'm going to show you how to get this in the Cartesian. They're like, yo, how would I ever think of that? Well, don't even expect me to. I'm just going to tell you how it's done. This is a lovely ellipse. All right. So anytime you have cosines or sines, it's going to be like either a circle or an ellipse. Or if there are some minus signs in front, it'll be a purple, but we don't deal with that. We don't deal with graphing that, at least. Okay, so it's kind of a weird one because you have all this trig stuff. So we're going to go ahead and make our table here. Just go along with me. Since we have a bunch of trig stuff, I'm just going to go ahead and graph at all of the quadrantal points, which is 0, pi over 2, pi, 3 pi over 2, and then 2 pi, because we have cosine and sine, and they're just going to start repeating themselves if I go beyond that. So I'm going to do 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so if I plug in a 0 for x, I'm going to get 5, because cosine of 0 is 1 times 2 is plus 3. For the y value, it's going to be negative 1. Pi over 2, I'm going to get just a 3 on the x over there. Look at my time. I need to beat that 15 minutes. Otherwise the video shuts down. So just trust me on this one. I'm just going to just copy the chart down I have right in front of me, because I need to get this done within 15 minutes. Otherwise the video shuts off. Okay, so when I go ahead and plot this, I'm going to go ahead and go 1, 2, 3, 4, 5, down 1, 1, 2, 3, up 2, 1, down 1, 3, down 4, and then again, so we start here, make this as an ellipse, and again, we're going in this direction. So I just draw those little arrows to let us know that, hey, we're going in this direction. Okay, we don't necessarily have a starting point for this one. So what we're going to do here is the crazy idea of solving for cosine, solve for sine. Okay, so I'm going to solve for both of them. So I'm going to get x minus 3 equals 2 cosine of t. So I'm going to get x minus 3 over 2 equals cosine of t. And I'm going to kind of leave that for right now. Go ahead and solve for the y one. And then, well, the sine, really. So y plus 1 equals 3 sine t. And then y plus 1 all over 3 equals sine of t. Okay. So the only equation that I know that we can use for sine and cosine is sine squared plus cosine squared equals 1. That's an identity, right? So what I'm going to do is I'm actually going to square these and input this here and input this here. So I'm going to get y plus 1 squared all over 3 squared, which is 9, plus x minus 3 squared all over 2 squared, which is 4, and that equals 1, which is our equation of an ellipse. So doing derivatives and stuff like that, and integrals and area, is so much easier to do with this than it is with this. So this is the reason why we learn about parametric equations. And we didn't do any calculus today. We didn't do any calculus. But I'm prepping you because calculus is next. All right? And that's it for this video.